Hi, my name is Jacob Wojciak, and I'm a senior software developer working for AWS.
Hi, I'm Tim Bray, and I'm a principal engineer who helps out with a bunch of services, including the messaging services. I'm just here for color commentary. Jacob will be driving today. Take it away, Jacob.
So what we're going to talk about today is when you're building modern applications running in the cloud, you have the three main pillars which you use to run your software. The first one is compute, whether you're running on your own hardware or your software is running on EC2 instances, or maybe you're completely serverless using Lambda. The second one is database, where you persist the data. Examples, MySQL database, DynamoDB, or something completely third-party like Cassandra. The thing that we're going to focus on today is the third pillar, which is messaging, which is like the glue that connects the pieces together. And when we talk about messaging, the most important concept in messaging is a message which is sent between software components. So it's the way you should think about it. It's higher level than an IP packet. And unlike emails, it's not sent between people, it's sent between software components. So messaging deals with passing messages around. Here's an example of a message that represents a booking for a hotel system, and the developers decided to represent the message as in the JSON format. And it's up to the developers to decide what the format of the message is. Here's the same message represented as an XML document. Aside from the message payload, typically you also can include key value pairs of message attributes. And the question that sometimes arises is, okay, so what should I put into the message body, and what should remain as message attributes? And the answer is, it's up to you, but typically in the message attributes, you will put things that you want to filter on or route the messages on. And this is especially important when you consider that you can actually encrypt your message payload, and the attributes remain unencrypted.
Hi, this is Tim. Another thing that's worth mentioning is that inside the message, as you saw in those examples, you can have quite deep nested structures, but your message attributes are pretty well just named value pairs.
So the first thing, the first concept in messaging that is the most simple one and one of the most powerful ones is queues. What are queues? Queues are durable buffers for your messages. And they have pretty simple operations. One is you can obviously send a message to a queue, and once you get a confirmation that a message was stored in a queue, the message is supposed to be durable, it won't go away. And on the other hand, you have message consumers which will pull messages from the queue, process whatever needs to be done for the message, and then acknowledge that they are done, which actually will remove the message from the queue. So a queue is a buffer between producers and consumers. And in AWS, we provide you with a simple queue service for your queuing needs. We actually have two types of queues. The standard queue is something that was in our offering for the past many years. It gives you the ability to use easily highly scalable queues that scale as your traffic grows. When you send messages, whether it's 1 transaction per second or 100,000 transactions per second, you can expect the same level of performance and latency from a standard queue in SQS. But this elasticity comes at a certain cost, and that cost is sometimes you will get a duplicated message using a standard queue, and sometimes sporadically the messages will arrive out of order. So for our customers that don't want to deal with writing code that will deduplicate messages or ensure that they are processed in order, last year we've released a new type of queue called the FIFO queue, which comes with a limited throughput, so it's not massively scalable like the standard queue, but gives you the ability to process your messages exactly once in an ordered fashion. Now, when you think about ordered message processing, the question is, can I actually use multiple workers to work on perfectly ordered messages? And the answer is, well, if it's a single stream of ordered messages, then no. it has to be a single worker processing it. So to allow you to build scalable message processors with a FIFO queue, we've introduced the concept of message groups. And what we say is messages belonging to the same message group will be consumed in order. And then by introducing multiple message groups, you can actually scale your fleet of consumers.
One example of where you might want to do that is if you're tracking sessions coming off a website with a huge number of users interacting with the website. So you would just use the session ID as the message group. And that way, each individual user's session transactions would be processed properly in order, but you could still handle a huge number in parallel, interleaved, with no problem.
And what's nice about the message groups is you don't have to pre-create them. It's just a string tag you can put on any message, so you can use as many message groups as you'd like without any extra preparation. The second concept in messaging is publish-subscribe messaging using topics. The diagram looks similar, but if you look closely, every message that is being published to a topic will send a separate copy to each subscriber. So each subscriber to a topic will process every single message that was published to a topic. In AWS, we provide you with an Amazon Simple Notification service, which allows you to connect a topic to multiple destinations, types of destinations. One of them are Lambda functions, the little serverless pieces of code that you can run in the cloud. You can connect a topic to an SQS queue, and you can also connect a topic to an HTTP endpoint where SNS will keep calling your APIs to deliver the message. And in both cases, both in SQS and SNS, we provide you with high durability of messages. We store each message with multiple copies. So when you send a message either to a queue or a topic, and you see an OK from that call, it means that you can be sure that the message will be delivered to your destination.
Jacob, they say you're a little quiet. Maybe you could lean a little closer to the mic. Thanks.
Okay. SNS also, and one thing I also wanted to mention here is both SQS and SNS are built per request, which means that you can create as many queues and topics as you'd like, and you're not paying for, if you're not using them, you're only paying for actual calls made to those topics and queues like send and receive. The third concept in messaging is message streams. So what are message streams? Message streams are ordered. When you send a message to a stream, it gets appended to the end of the stream. They typically also allow you to use multiple streams called stream shards or partitions, depending on the streaming product. And the question that you could also ask is, so what is the difference between a stream and a queue? And the main difference is, well, when you send a message to a stream, it is persisted. And when you read it back, you actually open like a cursor or an iterator on a stream. And you then decide how and when to move the iterator forward and backwards. And in a stream, when you do not delete the messages, they are persisted for a pre-configured time. So when would you use one and when you would use another? You should use queues when you can process your messages independently, and when you're done, the message is deleted. You should use streams if you want to analyze a sequence of items in a stream for analysis, for incremental differences between the items, or if you want to run multiple analysis on the same stream using multiple processors. And in AWS, we offer streams through Amazon Kinesis, which is a highly scalable service that allows you to provision multiple shards for a particular stream, and each shard has specific limitations of throughput and send rate.
The numbers on that at the moment are for each Kinesis shard, you can support up to 1,000 messages a second or 1 megabyte a second, whichever comes first. And you can put as many shards on as you want. There are customers running streams with thousands and thousands of shards. The other nice thing about Kinesis is that you can take out more than you put in, twice as much, in fact. So you can have 2 readers reading the stream and keeping up with it as fast as it goes, which is very, very useful in many applications.
And the one extra difference here is when you create a shard in a stream, it's actually provisioned, so you pay for each shard hour. So it's not per request anymore. Okay, let's look how using a queue can help in your software architecture. Let's imagine a hotel booking service. You have a website, the customers are connecting through the internet, the calls go through a load balancer, and the calls go to a fleet of web servers handling your traffic. Now, when someone actually makes a booking for a hotel, there's a second layer of service, microservice dealing with the bookings, and it sits behind another load balancer. And the booking service itself uses a relational database as the data store. And if you look at this diagram closely, most of the traffic to the website is browsing through the offers, and there's a lot less traffic going into the booking service when someone actually makes a transaction and books a room. So what can go wrong in this situation is you launch a huge campaign and with promotions, and now your customers are booking hotels at a rate that you were not prepared to handle. And because there's a huge number of web servers, they can send a lot of requests to the second layer of booking service, which is not really prepared to handle that load. And what can go wrong is your relational DB can start failing some requests or timing out on them, which turns out like you will propagate these errors back to your customers. So one solution that you could do here, and where messaging comes in handy, is you can replace the load balancer with an SQS queue, which will absorb any traffic coming into it. And the booking services behind it, talking to the database, can consume the messages in the backlog at the rate that they are comfortable with, that the database can keep up with. So this kind of protects you from this capacity mismatch between the layers in your service, when one layer can spike up traffic and the other one cannot handle it.
Another example of this, for those of you who've gotten into the serverless space, is using Lambdas. Now, Lambdas are outstandingly scalable. They can go from 10 functions per second to 10,000 functions per second very quickly. However, most databases cannot do that, can't go from 10 to 10,000. So it's actually possibly an anti-pattern to make database update calls directly from Lambda functions. And once again, you do the same thing that Jacob just showed, is what you do is you handle requests and events in your Lambda functions and drop them onto an SQS queue, and then you deploy enough readers against the queue to handle as fast as possible without overloading your database. So it's a general pattern. Another thing that Jacob mentioned in passing that I wanted to emphasize is durability. These are designed with the usual AWS techniques of replication across geographically separated stores. So when you put your message into a queue, it's durable. It's not going away, and you can count on that.
Let's actually see how it all works in a demo. I've pre-recorded a video that will show how using just a few lines of code, you can send messages to a queue, consume them, keep track of it, and how the queue behaves in that scenario. Okay, so here's an example program that will send messages into a queue. We call it sender. You pass the queue name as the argument. In one line, you create an SQS client to talk to our service. And we call one simple API to create a queue. And now the sender will keep spinning in a loop. We generate a new unique message. We send the message to SQS using a one-line statement and also measure the time, how long it took. And we print out some statistics on the screen. And here's the message we will be sending. It's just a piece of text with a random identifier. Here's the receiver code. So the prologue of the code is the same. We pass the queue name, create an SQS client, and create a queue. Calling create queue on an existing queue is a no operation, so it's safe to do so. And now we're going to spin in a loop, call receive message, and we'll be asking for max one message from the queue, and we're willing to wait for up to 1 second to get it. We're making the call here. Let's check if we got any messages. If the queue is empty, the collection will be empty. And now, if we got the message, let's simulate processing the message, which is supposed to take some time. And when we're done, we will call delete message. This is the acknowledging mode of the queue, where only when we're done, we're deleting the message from the queue. And also printing some statistics. Here's our worker. The worker will simulate that something takes 50 milliseconds to process. So it's just sleeping here for the purpose of this demo. And the third program is showing you how you can, again, like create a client, but now ask SQS about the statistics of the queue, and we will show on the screen the number of messages in the queue and the number of messages we are currently working on. So let's see this in action. Bottom left, there's going to be the status program giving out the statistics of the queue, and we can see the queue is empty. On the right, we're going to launch receivers. And at this point, because the queue is empty, the receivers will just keep waiting for a second and not getting any messages. Let's launch all of the receivers on the right.
There's nothing magic about Java. This can be written, of course, in any language that has the AWS SDK.
Yep. Now, on the left-hand side, we will launch senders. And immediately after launching a sender, you will see that the situation will change. The workers on the right are now immediately getting messages and processing them. You can see that the sender, on average, is spending less than 10 milliseconds sending a message to a queue. So it's a low latency operation. The same goes for receiving. It's less than 10 milliseconds to receive a message. And you can see that the sender is like spinning in a tight loop. So he's sending very fast. On the receiving side, we're waiting 50 milliseconds. So you can see on the bottom left that the queue size is growing. The receivers are not keeping up. And now, even if we launch multiple senders, their behavior, and because we're using a queue, they still have low latency. They can send messages at a high rate, and the queue in the middle absorbs all of the extra traffic that is going into the system. And what's nice about using queues is even when you stop all of the receivers, the senders are not affected. They still can keep sending messages into a queue, and the queue just keeps accumulating those messages in the backlog. So you can actually even have like a planned downtime of the receivers to upgrade the software. Let's resume the receivers, and they immediately go back to processing messages. And we can now stop the senders and see how the backlog of the queue is getting drained by the receivers. So the receivers are still receiving even though the senders are out. So we've completely disconnected the senders and receivers. They are talking to this very scalable and dynamic buffer of a queue in the middle. Okay, let's get back to the presentation.
Actually, Jacob, a couple of things. I noticed when in your code there, when you were calling the APIs, it was send message and receive messages. So I assume it's possible to process multiple messages at once. And in fact, possibly that's a best practice.
Yes, so we also have batch APIs. You can send up to 10 messages in the same call or receive up to 10 messages in the same call. And this will drive the cost of using the service down because it's a pay-per request and you're making less requests by using that. If end-to-end latency is not your biggest concern, then you can also use our async buffered client that we provide as part of the SDK, which will do the batching for you. Like you can send single messages and it will gather up multiple calls to send a single batch request. Okay, let's get back to the slides.
One more thing.
Okay.
I noticed that when you killed the receivers, the queue size started going up. Actually in quite an alarming way. And Christopher, who's watching the webinar, asked, "Is there any limit to the queue size? Should we be worried about that?"
So actually, there is no limit to the queue size. The only limit is how long is the message allowed to stay in a queue, and the max that we provide is 14 days. So you can survive like an outage of the receivers for up to 14 days. And so unfortunately, I don't have enough screen space to launch thousands and thousands of senders and receivers, but SQS can easily handle a huge scale of sends and receives.
In fact, I seem to recall hearing the team talking about situations where some customer would have literally 1 billion or more messages sitting in a queue.
Let's look at the second example. So imagine you have a hotel booking service and your boss comes up to you and says like, yes, like our website is super nice, but when a person actually books a hotel, they have to wait up to 3 seconds and there's a spinner on the screen and it's not a good experience. So obviously you want to improve the situation and you look at where do we actually spend time while doing the hotel booking. Turns out that the actual database operation is fast, but the extra steps are taking a long time. So one of the things that you could do is, okay, let's break it down. And on the synchronous code path, let's do the store in the database, and let's just launch a separate thread. Let's say it's a Java process. Let's launch a background thread to do the extra processing that needs to happen in the background. And it's all nice, but the problem is, if it's just a background thread in your existing process, what will happen if your Java process goes down because the machine had a problem or there was an out-of-memory issue? Basically, you now have lost work. You already stored in the database that the booking has been done, but all the extra work has not been processed yet. So you can have lost work. And now, if you have this case, then it's better to just use a queue for asynchronous tasks. So in the synchronous code path, you mark the booking as completed in DB and store the work item in a asynchronous work queue. And you have a background poller that keeps receiving tasks from the worker queue, processing all the extra work, and then deleting the message when it's done. So even if the worker dies, when you resume the operation, there is still a message. You will process through it and complete the work.
Jacob, we have about 5 people on the webinar who've all asked the same question, which is, what's the limitation on message sizes?
Currently in SQS, you can send messages up to 1/4 MB, 256 kilobytes. And we also provide like an extended client that allows you to send messages almost any size by storing the message bodies in S3 if they exceed the configured size limit. So you can just replace the standard SQS client from the SDK with the extended client, and you get processing of extra large messages just by design for free. For free meaning no extra development effort, because you will be paying for the stores in S3, obviously. So here with the background worker, the question is, okay, how should I configure my background queues for the tasks? So one approach is to have a queue per worker. This is a little bit risky because if a worker goes down, there's no one to process the items from this queue. But it's still like a nice option if the asynchronous task that you need to complete needs access to the local resources on that booking service host. For instance, there are some files on disk that only this machine has, and the background task needs to access those files. But my recommended approach would be something like this, where you have a single queue for backlog items, and any worker can then process the background task and complete it. Okay, and let's look at a third example here. Let's say you've done all the work and you're building a modern service. You've broken down the responsibilities into microservices. So now you have multiple services that are interconnected to process the hotel booking. And when a booking happens, you need to notify a small Lambda function that will email the notification about the booking that has been made. You make a call to your booking partner that the booking has been made. You send a message to a finance queue, and so on. And in this scenario, you have to implement the code yourself to talk to all of your parties. And it makes it really hard to add the 5th or 6th or 7th integration at this point, because it's you that have to go back and modify the booking service code. And there's an extra complication, like what should your code do if you fail to call the external partner? Like, it's now on you to keep retrying it or fail. How can you roll back? Like, those are the hard questions that you would have to solve in your own code.
In particular, what happens if you get throttled? This happens when you talk to cloud services. Sometimes it's just busy and says, call me back. And you're going to potentially end up dealing with multiple throttle scenarios at once in parallel, which can lead to some pretty nasty code.
So a nice way to decouple the booking service from its dependencies is to introduce a topic in the middle. So if it's an SNS topic, then you configure it once, you subscribe the Lambda email notification service just once, you subscribe an HTTP subscription for the external partner integration just once. So you just configure it once, and now whenever a booking is being made through your service, you publish it to an SNS topic. That call immediately completes, like it's very low latency, so your booking service gets an OK. And asynchronously, SNS will make sure that this notification will be delivered to all of your subscribers. Even for integrations with SQS, SNS says we will always deliver messages to the SQS queues. We will keep retrying until it succeeds. For integration with HTTP endpoints, which are like software that you are running or your partners are running, you can configure a retry policy, how long the call should be retried, at what rate the delivery should be attempted, and so on. And you will also can be notified if the HTTP endpoint actually failed all of the retry attempts, and you will get a notification about the failed delivery. So we've talked about SQS and SNS briefly. There's more features in both services. Let's start with SQS. We support long polling. What is long polling? Okay, imagine you have a queue and you have an API to access this queue. And your use case is, I want to process the messages as fast as they arrive. If you only have a simple receive call, this means you would have to keep calling receive in a very tight loop, never pausing because you want to get the message as fast as you can. The opposite would be kind of push delivery, where you would say, okay, if there's something in the queue, please call me back and let me know so I can actually process the message. Now that's risky because if there's huge traffic going into the queue, you would be overloaded by those notifications about messages in the queue. So long polling is actually the proper solution to this problem. And this means that you make a receive call to a queue and you're saying, I'm willing to wait up to like 20 seconds to get any message. And you keep waiting. And if the queue gets any message, the response will be pushed to you over this long poll receive call immediately. So it's very cheap because the connections that you're making are like once per 20 seconds. And you get instant pushes of messages when they arrive into the queue. That's long polling for you. We also support server-side encryption. And it's very easy and convenient to use. You just configure that, flip the switch on the queue, enable server-side encryption, you provide with a KMS key or use the default one, and voila, the messages are encrypted.
Yeah, there's a lot of flexibility in that. You can just say, turn on encryption and it all just happens. But if you want finer control of your keys or various combinations of key escrow and all that kind of stuff, that all works through the key management service.
The next feature is dead letter queues. So in a mature system, you have to deal with the edge cases and the errors that can arise. Imagine that the producer sent a message to a queue and the message was corrupted by the producer. It referred to a non-existing customer ID, or there were other like syntax problems with the message itself. And now on your receiving side, you get the message from the queue, you try to process it, but you just fail. Like you throw exceptions, you cannot deserialize the message, there's something wrong with it. The dead letter queues allow you to specify a policy on the queue that would say, please allow me to retry processing of this message up to, let's say, 5 times. And if I fail 5 times, move this message to this other queue so I can inspect it later. So it's like a sidelining process, and you configure the number of attempts. And it's a feature built into queues that is very nice to keep your service up and to see the messages that you keep failing to process.
Jacob, before we leave server-side encryption behind, somebody asked, how does server-side encryption impact messaging performance?
So it doesn't. Basically, we take the burden of encrypting and decrypting. We still provide low latencies for sends and receives. You can think about it as how much time do we need to spend on the CPU to decrypt or encrypt, and it's based on the message size. So huge messages will take just a tiny bit longer, maybe a millisecond or two, to encrypt and decrypt. The next feature is SQS is tightly integrated with CloudWatch, so you can see the metrics of the queue, the backlog size, the send, the delete rate, and you can configure alarms on it. This is super handy when you combine it with dead letter queues, and you just configure the dead letter queue, you set up a CloudWatch alarm to notify you whenever there's anything in the dead letter queue, and you can just relax and only be notified when things go wrong. And SQS is also tightly integrated with other AWS services as a destination. Any service that sends out notifications typically has SQS as a destination. An example is S3. You can configure an S3 bucket to send you notifications about putting items to a bucket. They will be delivered. They can be delivered to an SQS queue as a destination. There's also more in SNS. You've got multiple transport, multiple destinations that SNS supports. So we've mentioned HTTP, Lambdas, and SQS. SNS also supports emails and SMS messages and mobile application notifications. Although the new service Pinpoint is the new player in AWS to simplify delivering notifications to mobile devices.
Well, we're talking about SQS and SNS. Joris asked an interesting question. Are all the features of both available in CloudFormation, via CloudFormation?
Yes. SNS also provides customizable delivery retries for HTTP. So you get to decide how frequently the retries for HTTP delivery endpoint should happen and how many times. Provides you with failure notifications. If the delivery to HTTP endpoint fails or to a mobile device, you will be notified if you configure it. It's also tightly integrated with CloudWatch, so you can easily look at the metrics, how your topics perform, and set alarms on it. And it's also integrated tightly with other AWS services. Most of the services that publish to SQS will also allow you to hook up an SNS topic as a destination. And SQS and SNS have been around in AWS for many years now. We've got a lot of customers using both services and relying on them day to day to connect their services together. And we've got both customers that are kind of cloud native and build their entire infrastructure on top of AWS. An example is Lyft, which uses messaging applications to transmit messages between their services. And we also got like typically enterprise companies like Capital One on the board on moving into the cloud. They change their applications to stop using the on-premise messaging solutions and just move on into SQS and SNS to both lower their costs and improve the availability and scalability of their software.
You know, a couple of points. First of all, as we already mentioned once, SQS is one of the more mature services in AWS. It's been around for over 10 years, in fact. So we're talking pretty solid, very, very well debugged stuff. A more general point is that almost in any modern application, it's built on microservices. And it's a fact of life that microservices just don't run at the same speed and have the same latency and throughput characteristics. And there are very, very few modern microservice-based app designs that don't have a queue in them somewhere. It's just really hard to do anything complicated and high volume without having a queue in it somewhere.
One last thing about our customers. SQS and SNS are heavily utilized internally at Amazon, and actually Amazon Retail also relies on SQS for messaging to fulfill the orders of our customers. So the level of availability that you see from SQS is the same that Amazon Retail relies on. And if you'd like to learn more, here are 2 links to our product pages on AWS. You can read our docs. We have also some introductory material and some examples. And that's it from our presentation.